Welcome and study with Tanzania Institute of Education.
This lesson will be on cyclic quadrilaterals, but first, a quick recap on concyclic points. Concyclic points are two or more points that lie on the same circle. If we have a pair of points in any position, we can draw a circle that passes through these points. In fact, we can draw an infinite number of different circles through the same 2 points. We can also draw a circle through any 3 points, as long as the 3 points do not lie on a straight line. There is only one possible circle that can be drawn through 3 points, so it is called a unique circle. This theorem also means that the vertices of any triangle are concyclic. So, we could say that all triangles are cyclic. The circle drawn through the vertices of a polygon is called the circumscribed circle. So, what if we try to construct a circle that passes through 4 points? Are quadrilaterals cyclic? As you can see here, many different types of quadrilaterals are cyclic. They don't appear to follow any particular rules. They don't have to be regular, and the sides don't have to be parallel. How can we prove whether a quadrilateral is cyclic or not? The following theorems prove the properties that all cyclic quadrilaterals have, as well as prove whether a quadrilateral is cyclic or not. We'll start with proving. The sum of either pair of opposite angles of a cyclic quadrilateral is 180 degrees. In this diagram, ABCD is a cyclic quadrilateral and the centre of the circle is O. Draw in the radii OB and OD, which divides the central angle O into angle O1 and angle O2. Angle O1 is double angle A, so it is 2x. Because the angle subtended at the centre by arc BD is double the angle subtended at the circumference. Angle O2 and angle O1 form a complete revolution, so their sum is 360 degrees. This means that O2 equals 360 degrees minus 2x. O2 is double angle C because they are both subtended by major arc BD. So angle C is equal to 180 degrees minus x. But angle A equals x, so angle C plus angle A equals 180 degrees. The converse or reverse logic of this theorem is that if we are given a quadrilateral whose opposite angles are supplementary, meaning they add up to 180 degrees, then the quadrilateral is cyclic. We know that angle B and angle D on quadrilateral ABCD has a sum of 180 degrees. Let B equal x, so D equals 180 degrees minus x. If the 3 points A, C and D lie on a circle, we can sketch in the circle like this. Let's assume that point B does not lie on the circle. It could lie inside or outside the circle. If we found the point on AB that does lie on the circle, which we'll call B1, we'd know that it would form an angle that is supplementary to angle D and would be equal to x. But this will not work, since angle B1 cannot be the same size as angle B unless they are in the same position. Therefore, point B lies on the circle, and ABCD is a cyclic quadrilateral. This is called proof by contradiction. Do you remember learning the theorem about angles in the same segment of a circle? If a line segment subtends equal angles at 2 points on the same side of the line segment, the 4 points are concyclic. This is another way to decide whether 4 points form a cyclic quadrilateral. Theorems about cyclic quadrilaterals are useful at helping us to solve many different problems in circle geometry. For example, is a square a cyclic quadrilateral? We know that all of the internal angles are right angles. Therefore, all the opposite angles have a sum of 180 degrees, meaning they are supplementary. And since the opposite angles are supplementary, we have proved that all squares are cyclic. And what about a rhombus? Is a rhombus a cyclic quadrilateral? We know that the opposite angles of a rhombus are equal. But the only way that the opposite angles can be supplementary is if they are equal to 90 degrees. So the only rhombus that is a cyclic quadrilateral is a square. Let's look at another example. We are given a cyclic quadrilateral PQRS. The angles S and R are each equal to 80 degrees. We need to prove that PQ is parallel to SR. Angle P is supplementary to angle R because we know that PQRS is a cyclic quadrilateral. So P is equal to 100 degrees. The same is true for angle Q. Now we can see that angle P plus angle S equals 100 degrees plus 80 degrees, which equals 180 degrees. In other words, angle P and angle S are supplementary, but they also lie between the same pair of lines and a transversal. They are co-interior angles. So we can conclude that PQ is parallel to SR because the co-interior angles are supplementary. Final example. In this diagram, we are given that angle Q3 is equal to 30 degrees, and we need to find the sizes of some of the other angles. Angle S2 is an alternate angle to angle Q3, and the lines OS and QR are parallel. So S2 is equal to Q3 equals 30 degrees. Now let's find angle P. Angle Q2 is equal to 30 degrees because OQ and OS are equal radii, forming an isosceles triangle. So angle O1 is equal to 180 minus 60 degrees, which equals 120 degrees. Angle P is half the size of angle O1 because of the angle at center of the circle theorem, so angle P is equal to 60 degrees. Now we need to find angle R. PQRS is a cyclic quadrilateral. This means that angle R is supplementary to angle P. So angle R is equal to 120 degrees. In summary, you can prove that a quadrilateral is cyclic if you can show that a pair of opposite angles are supplementary. It follows logically that the other pair is supplementary as well. If a line segment subtends two equal angles on the same side of the line segment, then the 4 points are concyclic.